Okay, welcome everybody to our third session on in the data security track. My name is Paul Suhler. I work for KIOXIA Corporation. Did you hear how I pronounce that? KIOXIA. Everyone always asks me. This is about storage sanitization and why you do it, when you do it, how do you do it. I'd like to point out that unlike earlier sessions, we now have a mobile microphone, so I don't have to repeat questions that go on and on for long periods of time. And Eric will be the runner. So if you have a question, raise your hand and I'll direct Eric toward you. Okay, so what I'm going to talk about today is, here's a quick summary. The operators of data storage systems have legal obligations to protect their customers' data. And if they fail to do that, if there's a data breach, they can have very significant penalties. So what I want to do is explore some of the existing and the upcoming standards to show the best practices for how to sanitize customer data. Here's kind of a laundry list of what I'll talk about, but I'll just sort of skip over that. Okay, who are the players? I guess this is to establish kind of a vocabulary, and I didn't run this past anybody, so people may disagree, but vendor is the term I'll use for the manufacturer of a storage device. Organization is the operator of that storage device, usually the owner of it. And the user kind of overlaps with the previous one. The user is the entity that's associated with the data on that storage device. Now, I'm sorry. Okay, with regard to the user, it can be the organization that operates the device, storing their corporate data. It may be a customer of the organization that's renting out compute and storage from the organization, or the user can be kind of recursive. You may be renting time on a big storage system or data processing system, and they may in turn have their own customers. So user applies at a couple of different levels. So that's, user's a little bit squishy, but I think they're basically the people who have the, who own the data, or for whom that it is, yes, it is their data. Okay, so you have to avoid data breaches. And the way I define this, organizations have to ensure that user data does not escape their control. A data breach, and again, this is my definition, user data is made accessible to some unauthorized entity. Now that can happen a number of different ways. Somebody may steal the device. The device may be disposed of. For example, you've heard of surplus computer systems being sold, and then somebody buys it, and oops, there's all sorts of social security numbers and things on that. Okay, so that's stolen or disposed of. Another way a breach can happen is an attacker has gained access to the organization's system. So the device is in use and someone gets into it. And then finally, a data breach can be an authorized user of the system who accesses another user's data that he's not entitled to. Now, I don't know if that's a commonly used definition, but for me, that constitutes a data breach if this customer of mine sees this other customer's data. Either way, it shouldn't have happened. One way to avoid data breaches in many of these situations is to sanitize the device before it's repurposed, used, for another user of your organization, or before it's discarded. If it's a more or less obsolete device, you may just choose to get rid of it. And you want to sanitize it to make sure no user data leaves your control. So what is sanitization? The term that's been used is eradication of all user data from a storage device. So if it's eradicated, that means it must be infeasible to recover that data from that device, assuming you've got it totally under your control and you can do anything with that device you want to squeeze out the user data. There are different levels of attacks, and I'll talk about those a little later. Now, in terms of making it happen, there are commands on different devices. Typically, the command is called sanitize, and that will cause the device to eradicate some or all of the user data, depending upon how that particular command in that device command set is defined. Okay, so what's the process you have to go through? The first thing is take it out of the production environment. Now, you may do that physically by removing it from the rack where it's installed and putting it on a sanitization workstation. But the main thing is first, make sure that applications don't write it after you've sanitized it. So you have to keep it out of the environment. If the device is going to go back in use, and this may happen, you're sanitizing in place and then handing it off to a different, perhaps a different VM running a different user, then you can take the device offline logically, sanitize it in situ where it sits, and then hand it off to another one of your customers who is a different user. If it's being moved to a different system or discarded, then maybe at that point you move it onto a workstation and a technician performs the sanitization. Okay, so that's the first step. Wherever it is, the next step will be to issue the sanitize command. NVMe calls it sanitize, SCSI calls it sanitize in all caps, and ATA has all caps commands, and there are a whole bunch of them that have the word sanitize in the name of the command. Okay, you issue the command. You've got to make sure it completes successfully. If it hasn't, you would retry. If it's successful, then you verify that the data was actually eradicated. Typically, a way to do that is to put in some kind of a known pattern before, at least in places around the device, before you sanitize. And then after sanitize succeeds, you go back and look at those locations to make sure the data has changed. You can be, a sampling technique like that, or it can be reading the entire device, which with a 30 terabyte drive might take you a little while. Okay, what do you do if sanitization command reports a failure? Or if sanitization command failed, you can retry, okay? But if it doesn't work, or if you try to verify and the verification fails, then typically the next step is to destroy the device because you assume that you're not going to be able to get it to sanitize successfully. And then finally, you have to document what happened, that this particular device with this serial number was sanitized using, according to whatever process you have, and to make a permanent record of that. Because, for example, if somebody later claims that device turned up in a salvage yard and they were able to read data off of it, then you've got to be able to point back and say, no, we sanitized this device in this time, in this place. Yes, James. Oh. The microphone is en route.
If a sanitize is successful, what is the likelihood of a scenario where a verification of eradication is really necessary? I mean, what is the scenario where you'll find data on it even though it was successful?
Well, if it's successful and if sanitization succeeded and it was implemented correctly, then then verification in theory is not needed, but it's really good to have that verification in case there was a problem, just to prove that it actually worked. It depends how much you want to trust. And I'm going to come back and hit on this point in some of the variants. Yes?
Actually, follow-up question. So you said if sanitize was successful and it was implemented correctly,
yes,
then there is, not so much need for verification.
Yes.
So do we have a sense of how well is it implemented?
That's a really interesting question. It's not one that I can quantify at all. Eric, go ahead.
So in the earlier session, we talked a little bit about an initiative for the IEEE Conformity Assessment Program. And the whole idea behind that is in a case where verification is not adequate, having a scheme set up where vendors could bring in product and under the right conditions, proof of eradication could be determined. So you have a laboratory that basically goes in and actually gets into the hardware and is looking for any sort of data. The idea being that somebody is going beyond just the interface. They're actually trying to go into the mechanisms, the drive itself. The idea is if they don't find any data, then you've got, an additional assurance that has been put under the microscope, so to speak. And that may be adequate for the customers who trust but want to verify your implementation. Beyond that, it gets very difficult to sort of prove that the data has been eradicated. But that's sort of an additional step that we're looking at.
And I think I'm going to come back and talk about that a little later. Yes, Mike.
Go back to your prior slide. Wanted to just question that. Your second to last bullet seemed to say if verification failed, it was an operator. Your choice of may was interesting. But it becomes a responsibility of the operator. Why not the vendor? If sanitization fails, break the drive or, do something.
Well,
why did it become an operator decision?
Well, what this is saying is just the process that the operator of the drive has to follow. If it fails, then, they're going to go back to their vendor and say, what's going on here? So that's...
Sanitization fails, does that mean you write the drive as a vendor again? Yeah.
So
Yeah. Okay.
here's a perfect example of where you can have a sanitization you think succeeded, but this would turn up incorrect. You've got a hard drive connected to a PCI RAID card, and you think that RAID card is in HBA mode. So you think you're talking directly to the drive, when in actuality you're talking to a PCI RAID card, which is doing its own RAID thing and giving you a fake serial number. You issue a sanitize command, the array is actually intercepting those and not actually sanitizing the drive. Now, when the sanitization is complete, it's going to say that LUN had been sanitized. It'll give you the serial number of the RAID card's LUN, which theoretically shouldn't match the raw drive because you're not talking to the raw drive. But that's where a verification would catch it, and that's where a serial number check would catch it too.
Yeah. Okay, thanks. Let me move on. We ended up with a lot more people than it looked like at first, and so this discussion could be not just very interesting, but could take a lot of time. Okay, so let me talk now about the sanitization methods as we define them in IEEE 288. There are different methods. They provide different levels of protection. What's called clear, device remains usable, and user device cannot be read from the device. The next step up is called purge, and this is typically what the ATA, SCSI, NVMe commands are supposed to be doing. The device, again, remains usable, but not only the logical blocks, for example, that you can read, but any other place user data might exist, be it in caches, be it in deallocated blocks, wherever. Those are required to be sanitized as well. So that's the advanced laboratory attack. If the device were disassembled, you put the platters of a disk on a spin stand, or you put the chips, the NAND chips, and access them through that standardized interface, you would not be able to pull out any actual user data. That's the goal of purge, which is very different from clear. Even though a purge, if you don't disassemble the drive, you can't really tell the difference because you're still not able to read any user data that was written, but you don't have access to those other areas. Destruct, the device is destroyed, data can't be recovered from what's left of the media. Now, for each of these methods, there are, for clear and purge anyway, we have 3 specific techniques, and I believe that all 3, NVMe, SCSI, and I think, and ATA, of course, they all have these as options. When you perform a sanitize, you're going to do one of these techniques. Overwrite, the sanitize command will cause all accessible media to be overwritten. If it's a big device, that can take a little while. Block erase is really used for solid state storage because you have what's called an erase block. That can, in constant time, usually be set, I guess, typically to all ones. For example, if you're going to reuse a block for some, for a new write, you'll do this anyway, and then you can start writing it. But it's also a good way to sanitize. It is much faster than overwrite, but if you have a lot of erase blocks, and again, this can take a while. In some cases, the command standard may specify the data that is to be returned following a block erase. You may have some options in that command. Okay, cryptographic erase is only meaningful if the device is encrypting all the data as it is written. Erase is performed in more or less constant time by changing that encryption key. And if you make sure that the key is permanently changed, the old one is completely forgotten, then there, in principle, is no way to recover the user data without, as they say, boiling the ocean. And again, the command standard may specify the data that's going to be returned. And I'm going to return to a couple of these later and give some additional information about them. Destruct. We found in the existing standards that talked about sanitization, there were a whole bunch of different terms, such as crushing, pulverize. We settled on 3 separate ones, which are disintegrate, which means decompose the media, break it into small pieces. Incinerate, you burn it down to ash, or melt, and you reduce and liquefy it. Those are the 3 techniques for destruct that you'll find in IEEE 2883. Okay, so let's go back to verifying. Yes, Eric.
So just expanding on what you said a little bit, for these destruct methods that were deprecated, we determined that given the density of media, shredding, for example, and pulverizing, were not adequate anymore. You could actually recover, in some cases, full files. So, and this is actually an important detail that differentiates 2883 from, for example, the NIST 888. 888 is so ancient, it actually allows for these kind of destruct methods, which we've determined are not effective.
Yeah, that's the problem with as the size of a bit gets smaller, then you have to, if you're going to disintegrate, you have to do it to smaller and smaller sizes. Otherwise, you may end up with actually a lot of data on that little fragment. Another is, of course, for magnetic media, degaussing. Problem is that the denser the date, generally, as time goes on, people are using different recording techniques, and they typically require higher intensity magnetic fields to remove the data. And so, for example, if you take a degausser that works perfectly well on a LTO1 tape cartridge, if you try that on LTO7 or 8, it may not work. Is that, Glenn, have I got, okay, good. That span of generations is accurate. We are trying to advance here. Okay, so let's go back and talk about verification. The goal is the method is to, well, sorry, it's not a method, but the idea is to read the device to confirm that the user data does not remain. In particular, this is important for block erase and crypto erase. Those will leave the media, including any error correction coding that was on the media, completely invalid. Now, what happens typically is if you then try to read one, logical block that has been sanitized through either of these techniques, you'll get back a read error because there's some sort. It looks like there's some sort of media corruption. There are some workarounds. The front-end device can simply fabricate the read data and not even access the media, which kind of goes back to, do you trust your firmware? Or something that has been kind of kludged on was what's called additional media modification. So after you finish either of these techniques, the device then goes through and writes valid patterns onto all of the media so that if they are read, then you'll get back, a read command will succeed and it'll return what is a pattern that is typically defined in that command standard. It doesn't have to write every location on it doesn't have to write all of the media, but it does have to write, for example, any logical blocks that have been allocated prior to sanitization. Help is coming. NVM Express is defining a mechanism for reading media without reporting media errors. In fact, it's technical proposal 4152, post-sanitized media verification. It's in member review right now. So you don't have to do this tedious additional media modification step in order to at least be able to read something. Okay, depending on the device type, the sanitization behavior can vary. Now, there is not a single standard that's going to describe how sanitize commands and the destruct method work on different device types. So different organizations, again, I'll come back to NVM Express, SCSI, ATA storage interfaces, they have the same set of participants who try to make sure that all these behaviors align. And they've been through painful experiences in one standard or another, and we try to avoid making the same mistakes when we move these into the latest interface type. We have put in IEEE 2883 descriptions of these different devices' commands. For example, 2883, among other things, has a list of the steps to perform to prepare for, to sanitize, and then to verify. And we actually mention specific command types. Okay, what about newer devices that are going to be defined? We are hopefully, a couple of hours ago, we got approval from IEEE SA to proceed with work on Project 3406, which is standard for a purge and destruct sanitization framework, which would define how purge and sanitization should work at a fairly low level. And then 2883 can, in a future version, point to that. So we're trying to provide guidance, actually requirements for people who implement these commands, who define new commands and implement them. And not just commands, but also destruct methods. And I have to give credit to John Geldman of KIOXIA because he's the one who's been the proponent of this. Okay, so to come back to who do you trust? Customers have concerns. So like I said before, liability for a data breach can be in the many millions of dollars. It makes people who have hundreds of millions of customers' data, that makes them very nervous. In some cases, liability can exist in perpetuity. So if data is stored and 30 years down the road, somebody develops some kind of quantum computer that breaks AES, then you may be liable if all you did was a crypto erase, which at the time seemed like it would be adequate for the lifetime of the solar system, but suddenly it's broken. Okay, so what are real concerns? Well, is the sanitization firmware buggy? Has an attacker compromised the firmware one place or another before or after manufacturing? There's a software tool that the technician will use to sanitize the device. Well, is it really issuing the command? Did it really get back success? Did it really verify correctly? Good question. Or did the technician somehow make a mistake using the tool and thought they got the device sanitized, but in fact they didn't? These are things that the customers worry about. So if the operator doesn't have confidence in this entire process working, then they may decide to destroy the device. They may view that expense as worse, not as bad as risking a breach. Okay, well, why not destroy the device? Well, there are good reasons. Probably the person he's not here at the conference, John Michael Hands is someone who's looking into so-called circularity and reuse. We had some people referring to this, I believe, yesterday in one of the talks. So it's being raised in people's awareness, and I'd like to help raise it in your awareness. So destroying a device is wasteful from a number of angles. First, you can't use the device again. You're going to have, even if there was lifetime left on that device, you're going to have to go out and buy a replacement in order, to keep your own operation going. You can't just, if you destroy a device, you can't simply move it to a new system you're going to ship out. destruction costs money. It costs power, it costs labor, you have to build facilities to do this. And someone, I wish I could remember who, yesterday was talking about quantifying all of this in terms of the carbon footprint of doing all these different things. Also, the devices contain metals and other chemicals. You really don't just want to throw those things into a landfill. And I'd like to point out something I realized yesterday but didn't put in these slides. The sooner you can recycle something, convince yourself it's okay to reuse and send back up, the lower the cost of reusing it. If it goes all the way down through destruction, that's the highest cost path through the process. Because not only is it all those expenses, carbon footprint, whatever, to destroy it, you've then got to go buy a replacement. Nevertheless, some customers may decide that ultimately they really do have to destroy the device. Well, what do? Disassemble it. Component materials could then, in principle at least, be fed into different recycling streams. Now, I doubt it's even practical right now to take, for example, a BGA-attached SSD and render that down into its components. But certainly you can take a device in, say, a U.3 form, one of the U.3 form factors, and break that down into pieces. Pure metal sheet metal goes over here, et cetera, et cetera. There are some new standards in development that will provide guidance on how to disassemble a device, feed it into different recycling streams. So, what are the standards involved? The previous talk that I gave talked about the IEEE Security and Storage Working Group. We have one standard out so far, which is the standard for sanitizing storage. You've been hearing me say 2883. That was approved last year, and we're working on some follow-ons. ISO IEC 27040, titled Storage Security. Second generation of that, work led by Eric Hibbard, is nearing publication. And one thing we did was 2883 took and carefully defined a lot of the concepts, like the methods for performing sanitization, gave them clear definitions, and now 27040 can simply point to 2883. So it has additional requirements and guidance for different technologies and for practices. It covers not just media-based sanitization, but also logical sanitization, and a little bit about that later. But like I said, it does now point to 2883. So there's not overlap per se, duplicate or different definitions of the same terms. That was one of our goals, to get rid of that. The Trusted Computing Group, in its storage working group, has, I'm sure you've heard of the OPAL subsystem class specification or standard, and then there are other so-called SSCs. So these are some of the points in the standards environment. There are others. Everybody has heard of FIPS 140-3, part of NIST's cryptographic module verification program. The way they've organized things is that they don't perform the testing themselves, but they certify laboratories who will do it for typically the device vendor. And the device vendor may pay $30,000 and up to have a device certified. NIST also has various special publications. They cover different aspects of not just security, but also cryptography in particular, including algorithms. One of the latest things they're working on are algorithms that are resistant to attacks by quantum computers. For example, some of the big worries are around asymmetric encryption algorithms like RSA. Symmetric algorithms like AES, somewhat less. I think right now the best thought is quantum attacks on AES might remove one bit from the security. Whereas something like factoring large numbers could collapse completely. Over in the EU, there is a regulation called 2019/424, which is commonly known as Lot 9. That has references to you should perform secure data deletion, but it doesn't say what that really means. Now, the way we've gone with 2883 and 27040, those could satisfy that. So we would like to see the next revision of these regulations point to these other international standards. Verification. I think I've actually already talked about this, where crypto erase and block erase will result in any reads giving reporting a media error. There's a hack, like I said, to perform additional media modification, at least to have what is read off the back end return some data. But the new verification mechanism, at least in NVMe, will skip that media modification and allow reading the media without reporting errors. Now, one thing that was brought in by a company that makes actual memory chips is we do not want you reading our chip repeatedly, because if you do that, then you can see what you can accumulate and figure out what our uncorrectable bit error rate is, and that's highly proprietary. So one thing you'll see in this technical proposal that's in the works is we allow the controller to report different data each time the same logical block or portion of media is read. So you try to keep the media, the proprietary characteristics actually unavailable. Some of the other things that are happening, sanitization of subcomponents, not only sanitizing a complete logical unit or NVM subsystem or what have you. One good example is an NVMe namespace. A NVMe subsystem, a single SSD, may have multiple namespaces. The way people sometimes use these is you may have each virtual machine on a host may be given a different namespace. Each virtual machine may be running a different customer's application. And when you finish with one, you'd like to be able to make sure that namespace is actually sanitized, and then it can be handed off to a different VM. That's one of the use cases motivating the purging of a NVMe namespace. Ideally, and we're not sure where this is going to go because we haven't made a lot of progress on this, is other namespaces could continue to be written in red. That may or may not turn out to be economically feasible. There are some other twists on this, because the way the sanitize command is currently defined, it's supposed to clear everything. You've heard of perhaps of the persistent memory region. That has to be turned off. It's before you can even run sanitize. Controller memory buffer may have read or write data buffers that are used for IOs to other namespaces. So if you sanitize a single namespace, you're probably not going to be allowed to touch CMB or PMR, because you would you would terminate work that is ongoing using other namespaces. But like I said, this is very early, and we'll see where it goes. These are just my observations looking at that original proposal. Other things are encrypting at a finer granularity. The Opal specs, for example, used a single, in principle could use a single key for all of the device. There are other things in TCG that allow you to encrypt at a lower level, but now this has found its way into NVMe, and there's an approved technical proposal that's been published, ratified some time ago, and is available. For example, you may want to write a file that has data for only a single person with a unique encryption key, and that may be only a small part of the namespace. Then this technique was called key per IO, where a read or write command and some other IO commands can specify a particular key to use for whichever logical block or logical blocks are accessed by that command. How do you get the keys into the device? TCG has worked out the key per IO SSC. So the provisioning of keys was handed off to TCG to do. Definition of the commands was kept inside NVMe. This all presumes that the keys are not persistent anywhere except in a key management appliance, never inside the drive. In the drive, they have to be ephemeral. The key management interface protocol from the OASIS group has defined an interface between the host and the appliance. So what motivated this was a requirement from the EU. You may be presented with a legal order to eradicate the data for one particular person. So obviously, if you've encrypted the data with a different key for each different person, then if you can erase all the copies of that key, then it's impossible to recover the data off the device. But again, that leads to more questions. How are you going to prove that all the copies of the key on all your key management servers have been deleted? I gather that OASIS is working on that. But again, it's suddenly become a kind of a difficult problem because you can't simply look at the device. The keys aren't there anymore. How do you know if you give that if you give that device away or resell it or whatever, that somebody isn't going to find a copy of the key on a key management server somewhere and then access the data? One way around that, if you're going to dispose of the devices, possibly you add another level of a key, a single key that stays in the device and is not readable. If you want to erase the entire device, you change that other key. And then even if you re-inject one of the original keys, you're still going to get garbage when you try to read it out. But it's a difficult problem. Is there anyone here who's familiar with that work on trying to ensure that all copies of a key kept outside the device have been deleted? I don't know if, okay, so we don't have anybody who's really conversant with that, but it's a concern. Some of the other new directions. Customers need guidance on how to use sanitization. So we have one in the second major, well, the questions are, what are the risks of exposure of different kinds of data that you may have? What are the appropriate sanitization methods for devices that hold that kind of data, each kind of data? And what are the effectiveness, the economics, the environmental consequences of the different methods you would use to sanitize? So IEEE SysWig is developing a couple of new standards. One is 2883.1, and this is the one that's most active right now. It's called Recommended Practice for the Use of Storage Sanitization Methods, and it's essentially trying to explain how to use sanitization to meet your organization's needs. What we're almost done with right now is working out the right way to present to the reader how do you analyze the value of your data and the risks from data breaches for different kinds of attackers. I mean, you may have a script kiddie, you may have a nation state, and then there are people with different capabilities in between. And we try to give guidance for each of those for different sensitivities of data. The next project coming up after that will be 2883.2, and that's extending, discussing sanitization for virtual systems, for cloud systems, et cetera. The problem with those is they can scale up enormously, the amount of data. So some of the problems are a bit different, but that's going to be the next thing on our plate. Okay, a new standard is a project called P3406, and I think I mentioned it before. Sorry, this is my second talk in 2 hours. So this will provide requirements for standards organizations and implementers who define purge and destruct techniques. It's important for new storage technologies. There'll be, DNA storage, crystal storage, where you're using a silica-based material. These will have their own ways of doing destruct and possibly also purge. And again, you need to make the data recovery infeasible using state-of-the-art laboratory techniques. And there'll be some techniques that have to be deprecated. Like I may have mentioned before, AES may potentially in the future be broken. And in a case like that, we will have to update these standards to, get rid of the old, now broken cryptographic methods. Okay, we've talked about device certification and a bit about FIPS 140-3. The way it has worked, and I say this because several years back when I was at Micron, Mike Danielson, my boss, and I started inquiring in this direction how this might work. And we talked to a couple of companies, in particular Drive Savers and OnTrack. They told us, these are private testing companies, and what happened then is the purchaser of the device would typically bring them samples and have them they would perform a sanitization, and 80% of their customers wanted to pay for the most complicated, which is the advanced laboratory technique. After you've sanitized it, tear the device down, try to find any user data left anywhere on the device. There were only about 20% who would just say, just run the sanitize command and read over the interface. Anybody can do that. But not everybody has a lab where they can do serious checks. The device vendors, turns out some vendors were willing to help more than others. They would help explain, well, these are the regions where we put the retired blocks that may still have user data. These are tables, these are other things, and help them find where they needed to be looking for user data that might have leaked through the process. Other device vendors didn't help at all. But the bottom line was, after you pay these companies a bunch of money, they would provide you with certification that this device running this firmware met the standards that the private company had established. So we'd like to see that pushed into a industry-wide program, so you don't, which could then use these companies as test labs, but it kind of changes things. In the model that's been up to this time, it's the purchaser of the device who would pay for this. Are the device vendors going to pay for the certification? Obviously, they're going to have to pass the cost on to their customers. That's how it's worked with FIPS 140. The device vendors are the ones who pay the cost. And of course, there's always the problem, if you change your firmware, well, suddenly that device and that firmware, the firmware's changed, your certification is not valid. Now, if the change in the firmware didn't touch the, for example, encryption stuff, that the encryption functionality that 140 is concerned about, then it's much less expensive to get a certification for the new firmware on that same old device. SysWig is going through the IEEE Conformity Assessment Program, which has been used in the past. Eric had said in the previous session, typically to do certification of security of medical devices, and there are quite a few others. We're just beginning to explore this and try to see what we have to do to set up the program. Well, we know, and we've taken the first couple of steps in that direction. And that's it. So we have about 7 or 8 minutes. Questions? Yes, sir. Here's the mic.
So I'm not very familiar with all these standards and specs, but is there a problem with maybe falsification of records that you've sanitized to drive? Like, could you have a lazy sysadmin who just fills out paperwork saying, "Yeah, I did it"?
Sure, that's one of the other things that concern the people who are going to have to pay the fines. Yeah, Eric.
So to respond, directly to your question, think of when you're doing sanitization, so your organization XYZ, and you are sanitizing your drives, and that's saying they're being sold on eBay, and somebody makes an accusation that, oh, I've recovered data that I shouldn't have, and therefore you've got a data breach. If you have collected the evidence as part of your sanitization process, you have at least a chance to demonstrate that not us, somebody else because you can show that yes, we went through this process, and you've got materials. So you're doing this proof of sanitization. The records that you're keeping is really for the organization that's doing the sanitization. It's your safety net. So if you're faking it, and then there's a data breach, well, depending on how good the forensics and the lawyers are and how much money is involved, they may or may not ferret that out.
Yeah. But of course, a corrupt employee or incompetent employee is always a problem, but that's kind of a general managerial problem anyway. So, like anything, it takes oversight. More questions? We have another 5 minutes. Yes, sir. You're going to get the microphone in a second.
So why do we trust the software in dealing with sanitization? Why can't we take all the storage components, whether it's EEPROM, memories, NAND modules, and have a boundary scan to just make sure everything is wiped? Because ultimately, anything driven by software could protect some blocks with firmware images. I could have my files written there. Nobody would know. There is no way to access it.
Yep.
But data could still be there.
That's why it's, okay, Eric will probably want to answer too, but I'd say that's why you have a certification program. Okay, John wants to answer.
Well, I would just say you're going to have one heck of a FIPS 140 boundary issue.
But the sanitize command doesn't deal with security commands on each write. So a write 0 to that block could be hacked,
Oh, yeah.
right?
Yeah. And again, that's why you do certifications, which have to be looking at the firmware. Now, okay, so that said, I participated in years gone by in a couple of FIPS 140 certifications. We took the engineer from the security lab, we walked him through our code, we demonstrated everything, and my conclusion was, if I were dishonest, I could have fooled him completely. So it depends. Again, it's a matter of trust. Can you trust your employees? Can the test lab trust you?
Well, I'm coming from how do we convince the customers that yes, indeed, we are trying to say that the NAND package is completely empty.
Yeah. Well,
Yeah.
Thank you for transfer. One, the NAND may not be completely empty. One of the basic precepts of Sanitize is that it is likely that there are bad blocks. And the rule is that those are no longer available for allocation. So it does require some intelligence to review what's there. And there may be some things there which are not accessible through the interface by any means possible. Another part of it is that oh, darn. It was right at the tip of my tongue.
Mike, hold on. Mike, we want to get you on tape too.
The recording.
I think I wanted to confirm this. I don't think the interface matters because what I saw as part of Purge was that includes disassembly.
It has to be proof against disassembly and advanced laboratory techniques.
So it can't just be, heck, you could just use the deallocate command and you wouldn't be able to read it over the interface, right? But none of us considers that secure. So I think it's more than just, okay, you can't read it off the interface.
Right. If you're going to make sure it was correctly purged. Okay, Chris, we'll put you on hold. We have another question in the back.
Sorry. So a quick question about the bad blocks that were mentioned. So would this work around specification not be dealing with, specifying how the bad blocks or reallocated sectors should be handled in sanitization?
Oh, they do. And for example, the NVMe specification says those must never be readable. Now, if you can't guarantee that they were actually overwritten, then you have to guarantee that you're never going to use those again for any write data. And that they will never be... Sorry? Yes, if there is, right, so the question is what happens if there is a failure and some bad blocks are not cleared? In principle, the device must make sure that they are never readable again and they're never going to be used again. That's what the definition of the sanitize commands typically states.
You said in your first slide that devices that were disassembled and the media ran at the low level, you said that on your slide.
Yes, they can be read. Right, and
So Paul, I mean, one part of this is in the verification, if you determine that you've got lots of bad blocks and things of that nature, that may be the reason you destroy. So you may be attempting a purge, but because of errors that you can't deal with, then the ultimate sanitization method goes to destruct.
Yeah, and that's one thing that has come up. Perhaps we want to provide information on after the sanitize operation was unable to touch some bad blocks, and we can't guarantee where that information is gone. And so if that information were available, then maybe you decide to destroy the device. Okay,
and that was my
we're over time, so Chris, you're going to be the last one.
And that was my comment, is you always have to have the destroy in your back pocket, because in the lifetime of the device, over 3 years, 5 years, whatever, you're going to have devices that fail. When those devices fail, they may not respond to any SCSI commands. However, those devices are very likely repairable. So you're going to have to destroy them because you can't issue commands against them. You have to destroy them. So destroy's always got to be in your back pocket, and you've got to be ready to do it, because that's your standard answer to a failed component. That's the easiest way to exfiltrate data, is to pretend to be a repairman, go in, change out a failed drive, which it's got a lot of data on it. That's the thing that you got to worry about.
Yeah.
And you've got to step in between your normal service people who want to just take a drive and put a replacement in, to make sure that drive is put into a separate machine so you can sanitize it, or that drive is destroyed, or whatever method you need to do.
Okay, thanks very much, and I think that helps address the point that you were making. Everybody, thanks very much. I appreciate your attention. We're going to have the next speaker up in, I think, about 8 minutes. Thank you.